Hi everyone, I am Shantonu, a National Postdoctoral Fellow at IIT Mandi. I joined IIT Mandi about 6 months ago and it is a great pleasure to participate in this ANRF IIT Mandi Webinar Competition. I am especially happy to be part of this event because it not only provides a platform to present our research but also inspire in young researchers by showcasing the exciting science being carried out at IIT Mandi. My research focuses on the synthetic methodology development where our goal is to design reactions that are simple, sustainable and efficient for the synthesis and the late stage modification of biologically important molecules. Today, I will present our NRF-funded project entitled Electrochemical C4 Selective Alkylation of Pyridines, a sustainable strategy for late-stage diversification of the bioactive scaffolds. Now, when people hear the words electrochemistry and organic synthesis together, they often wonder how these two fields are connected. Since electrochemistry is traditionally associated with the physical chemistry, let me begin with a brief introduction of electroorganic synthesis. So, why are chemists increasingly adopting electrochemistry in organic synthesis? There are several compelling reasons. First, electricity can be generated from the renewable energy sources, making it an inherently greener reagent. Second, its reactivity is highly tunable. By simply adjusting the applied current or potential, we can precisely control the reaction pathway. Another major advantage is that electrochemical reactions are easy to monitor, often generate less chemical waste, and eliminate the need for stoichiometric oxidant or reductants. Last but not the least, the low cost reagent. The electricity is remarkably cost effective. If you look at the comparison shown here, the cost of the commonly used oxidants is significantly higher than that of electricity. In fact, electricity by far least expensive reagents among all the oxidants compared. So electrochemistry is not just a greener alternative, it is also economically attractive strategy. But this transformation did not happen overnight. The journey began with William Gilbert, who first recognized the electricity as a scientific phenomenon. Later, Luigi Galvani's famous experiment demonstrated the relationship between electricity and biological system. A major breakthrough came with Alessandro Volta's invention of the voltaic pile, which made continuous electrical current available and laid the foundation of the electrochemistry. Soon after, classical electroorganic reactions such as acetic acid electrolysis and Kolbe electrolysis were developed. During the 20th century, electrochemistry became an increasingly valuable synthetic tool contributing to many important organic transformations. Even Professor E.J. Corey utilized electrochemical methods in the synthesis of complex natural products such as pentacyclosqualene. More recently, electrochemistry has revolutionized modern synthetic methodology. Landmark development includes electrochemical CH activation, electrochemical cross-derivative coupling introduced by Zhu and Lei in 2017, as well as groundbreaking reactions such as electrochemical Birch reduction and cross-electrophilic coupling are also there. These examples clearly demonstrate that electrochemistry has become an integral part of modern organic synthesis. Now let me briefly show the reaction setup where this transformation actually takes place. There are four common electrochemical reactor designs. The most widely used is the undivided cell, where both the anode and the cathode are immersed in the same reaction compartment. The second is the divided cell, where two electrodes are separated by porous fluid membrane to prevent the mixing. In addition, there are undivided flow cells and divided flow cells, which are particularly used for the continuous flow synthesis. Now, for our work, we use the undivided cell as it provides a simple, practical and efficient reaction setup. Here you can see our electrochemical setup, the electrodes with Teflon cap and the undivided cell and Electrosynth 2.0 workstation, which precisely controls the applied current throughout the reaction. Let's move to the chemistry that we aim to develop. Our target is the selective functionalization of pyridines. Why pyridines? Because pyridine is one of the most important nitrogen containing heterocycles in medicinal chemistry. As shown here, among FDA approved drugs containing agent scaffolds, pyridine represents the overwhelming majority. Consequently, methods for the pyridine functionalization have become an active area of research. However, achieving site selectivity remains a major challenge. While C2 functionalization is well established and C3 functionalization has also been extensively explored, direct C4 selective functionalization is comparatively underdeveloped. Most reported methods rely on the installing a blocking group to mask the more reactive position. This requires additional installation and removal steps, reducing the overall efficiency of the synthesis. Although several alkylating partners have been reported, a simple and direct strategy for C4 selective alkylation is still highly desirable. Our central hypothesis is to use electricity as the reagent instead of conventional chemical oxidants. Under electrochemical conditions, we aim to generate a reactive intermediates from the agent substrate at the cathode. Simultaneously, a hydrogen atom transfer reagent will activate the unactivated hydrocarbons to generate the alkyl radical. Then the two reactive intermediates expected to combine selectively, furnishing the desired C4 alkylated pyridine or agents under the mild sustainable reaction conditions. Looking ahead, we envision applying this strategy to late-stage functionalization of the biologically relevant molecules, including compounds such as nicotine and bisacodine, as you see here. Furthermore, we plan to extend this methodology beyond pyridines to other important agents, including quinolines, pyrazines, pyrimidines, etc. Optimization of the reaction condition is currently underway, and we are optimistic that this strategy will provide a general and sustainable platform for selective agent functionalizations. With that, I would like to conclude. I sincerely thank my mentor Dr. Abhishek Dewanji for his continuously guidance and invaluable scientific discussions. I also thank all my members of our research group, ANRF for generously funding this project, and IIT Mandi for providing the research facilities.